covering titration. Titration is a lab neutralization reaction used to determine the concentration of an unknown acid or base solution. We were talking recently about neutralization and writing neutralization reactions. In a titration, we are going to use neutralization reactions and mathematical proportions that we know from those reactions to determine concentration. In titration, you're going to have a standard solution. A standard solution is a solution of known concentration. And that concentration, as usual, will be given in molarity. It could be an acid or a base. It depends on what our unknown is, which we choose. If we have an unknown acid, our standard will be a base. The titrations that we are going to do in class will have unknown acids, so we will be using a standard base. Making a standard is a tedious process where you have to make sure that your molarity is very carefully measured and calculated. The standard solution will be put into a burette. Remember, burettes allow us to very carefully and precisely measure volume, specifically in milliliters. We will put our unknown in a beaker. Typically flasks are used, but for our titrations we tend to use beakers. And with that unknown, we will be putting an indicator. pH probes can also be used if they're available to give a slightly more exact result. We will know two things about the standard. We are going to know the molarity of the standard, or the concentration of the standard. We are also going to know one thing, we'll know the molarity of the standard, and we'll also know the volume, typically in milliliters, of the standard that we use, which we're again going to be measuring in our burette. We're going to know one thing about the unknown. You may have a typo in your packet. Please fix that. We will know one thing about the unknown, and that will be the volume of unknown that we are titrating, typically in milliliters. Titrations could be done in liters, but liters are kind of large, so it's not. Typically, they're done in milliliters. And again, one of these is going to be an acid, one of them is going to be a base. Most typically in our labs, we have an unknown acid and a standard base. Again, what this actually is a lab neutralization. So we use an indicator or pH meter to determine when neutralization has occurred. So what we're actually going to be looking at, I'm going to go back here for just a second. In this beaker with the unknown, we're going to want to know what that pH is. We have some idea of that pH, which we're going to determine from an indicator. And then when we add the base to that, if this is an acid, when we add the base that is from our standard burette, we're going to gradually bring that pH up. And when we get to a neutral point, we hope to know that with our indicator solution, we will then know essentially that we're done. So an indicator or pH meter is used to determine when that neutralization has occurred. The equivalence point is when the amount of acid and base are equal. This is essentially when neutralization has occurred. That means you've neutralized the solution. And when you've neutralized the solution, you know that your amounts of acid and base are equal to each other. So you're then able to solve for your unknown. If you have a pH meter, you can actually do a really nice graph that shows the progress of a titration. And this has kind of a strange shape to it because of that logarithmic relationship that pH has. In this particular graph, you'll notice that you have a volume of base on the bottom. This this means that we're actually adding base. And as we are adding that base, we are reading the pH in that beaker where the unknown solution is. So this pH over here is what we're measuring in our beaker or flask that contains that unknown. So our starting solution had a low or acidic pH. As we add base to it, the pH increases. When the pH reaches 7, we call this the equivalent point. In this particular example here, we are looking at an unknown acid with a standard that is a base. I can tell this for two reasons. I can tell because in the process of the titration, my pH is increasing, which means I'm adding base to acid. And I can also tell because they're telling me on the x-axis that my volume of base is increasing. Where your neutralization occurs can also be referred to as the end point. You do not need to write this down. The word end point means you are done. It's ending. And this is really what we're going to achieve. It's not always exactly the same as the equivalence point, but the end point is where the indicator changes color. Again, you don't really need to write that definition down. Just keep in mind that you're trying to get to a point where neutralization has occurred. In this example, as we just mentioned, we are adding a standard base solution to an unknown acid. Since we already know molarity and then we will know volume from measuring about the base, we know volume of the acid, we can then solve for molarity of the acid. We're going to do this using our titration formula. Titration formula is on table T. Titration formula will work for neutralization problems. You may remember we used the same formula for dilutions. We're just applying it in a little bit of a different fashion. Molarity of an acid times the volume of an acid equals the molarity of a base times the volume of a base in a titration. Some things to note. Molarities must be in molarity. Volume can be liters or milliliters. Most frequently it will be liters. Your volumes need to be consistent when you plug them in. You can't plug in liters for one and milliliters for the other one. So a typical example, how much 2 molar NaOH is needed to titrate or neutralize 20 milliliters of a 3 molar hydrochloric acid solution. Sometimes it's nice to start with a neutralization reaction. As you get into these a little bit more, I'm going to show you a shortcut that allows you to skip this. But what we're actually doing is we're taking NaOH, we're reacting it with HCl. Our H and our OH are forming water, and we have leftover NaCl. And this balances out. We got 1 sodium on each side, 1 oxygen on each side, 2 hydrogens, and a chlorine on each side. So we don't have to do anything else with this reaction. Now I'm going to go back and I'm going to look at what I know from the problem. My first number given is my molarity of my base, which I know from that OH. And that's 2 molar. I know also my volume and my molarity for my acid. So my Ma is 3.0 molar. My Va is 20 mils. My unknown is my Vb. And that will come out in milliliters since my volume of my acid is given in milliliters. So I'm going to write my formula. MaVa equals MbVb. When it says here account for any coefficients, this has to do with certain acids and certain bases that are what we call diprotic or might have multiple hydroxide ions. We discussed this in neutralization. This particular problem does not need us to account for any coefficients because there's no coefficient next to the hydroxide. There's just a 1 there. And there's a 1 here next to this H. So we don't need to worry about that. So now we're simply going to plug into our problem, and we are going to solve. So we're going to plug in Na, 3 molar, times my Va equals my Mb times Vb. Should give you a volume of base of 30 milliliters. Now, I'd like to show you a problem where you are going to be concerned with a coefficient. A 25 milliliter solution of H2SO4 is completely neutralized by 18 milliliters of 1.0 molar sodium hydroxide. We want to know the molarity of the NaOH. If we were to write a neutralization for this, what's important to keep in mind here and you may remember this is, since we have these 2 hydrogens right here, we actually create 2 waters, and it requires twice as much base. So we need twice as much NaOH so we can get all those OHs to cancel out the 2 acidic protons that each sulfuric acid brings to the table. So we're going to have to account for that in step 3. So I'm going to go ahead and I'm going to list my knowns and unknowns. I have my first number given is a volume of acid, which is 25 milliliters. This is completely neutralized by 18 milliliters of Bb of 18 mils of 1 molar sodium hydroxide. So I'm going to write my formula. MaVa equals MbVb. By accounting for coefficients, what I mean is I need to tell people that each mole of my acid gives me 2 acidic protons. Mathematically, this will double the amount of base that I need, which is what I want to do, because it's going to take twice as much base to cancel out this acid. So the reason this works, I look at my acid, which is H2SO4, and I look at my base, and I write down my formula, and I just want to say, hey, my moles of acid stuff is doubled because of that 2 right there. If there were a 3 right there, I'd bring down a 3. If I had calcium hydroxide, CaOH2, I would bring down a 2 over on the other side. We'll look at some examples of that separately. Now that I have my formula, I am able to plug in and I am able to solve. So I'm going to bring down my 2 MaVa equals MbVb, 2 times Na times 25 milliliters equals 1 molar times 18 milliliters. Punch this in your calculator, and you should get 0.36 molar. Just a brief explanation on why this actually works. We need to make sure that on this side, on the acid side, we're accounting for the fact that we have 2 times as many hydroxides. 2 times as many protons. This guy right here will be canceled out by that guy. This guy right here needs somebody else to cancel him out. By putting a 2 on this side of the equation, mathematically represents that, and will double the amount of hydroxide that, or whatever base I have, that I mathematically come up with. There are 2 quick mistakes that I need you to fix. In your first try on your own problem, the molarity of your acid is 3.00 molar. In your second problem, the molarity of your acid is 2.00 molar. I apologize for leaving those off. Take a moment right now and solve these. I'm going to pause them, write up the answers, and when you're ready, you can go ahead and check. So you can go ahead and check your answers. On the first problem, we don't need to account for any coefficients. There's just one hydroxide in NaOH and one hydrogen in hydrochloric acid. When we plug in all of our numbers, we get a molarity for our base of 4.20 milliliters. And our second problem, because we have a 3 in our acid, it's creating 3 acidic protons for each mole of acid that we use. So we are putting a 3 into our calculation on the acid side. Plug in each of our numbers, we should get a molarity for the base of 5.22 molar. If you flip to your titration calculation homework, what is important to keep in mind that I do want to note before you work on these, whenever you have to deal with a base, for example, number 3, famous Jeremy Thurston problem, you've got MgOH2 and hydrochloric acid. In your MAVA formula, we do only have a 1 here, so we're not going to put anything on the acid side. Because of the 2 on our basic hydroxide, we are going to add a 2 over on our basic side. So you could have to add something if you have a coefficient with your base.